It's a pleasure to introduce Dr. Lara Pudwell, now recently a full professor, who will talk about pattern avoidance in parking functions. As usual, if you have a question, please unmute yourself and ask it. Otherwise, mute yourself. And if you have no background noise, you're also encouraged to unmute, to stay unmuted so you can laugh at Lara jokes. As usual, the official part is 48 minutes, and after that, people are welcome to ask informal questions. Go ahead, Lara.
Okay. Well, Daron, thank you for inviting me to visit the seminar again. It would be great to be in person, but this is a great still way to connect and talk about exciting math. This project is a new project in the last 6 months with Ayomikun Adeniran, who is at Colby College in Maine. And the backstory is Ayo is an early career faculty member, and he wrote me and said, I'm figuring out my first project since grad school and having a mentor telling me what to do. And you've been thinking about pattern avoidance for years. I've been working in parking functions. Do you know if anyone's done pattern avoidance in parking functions? If so, who? And if not, do you want to think about it with me? And this was perfectly timed at the beginning of a sabbatical. And so I wrote him back enthusiastically and said, yeah, let's think about this together. And so this is the story of that collaboration in the last 6 months. This is really a mashup of the area I'm used to of patterns and permutations and what Ayo is used to in parking functions. And so I kind of have a two-part introduction. First, I will make sure we all have the same notation for patterns and permutations. Then I'll tell you how we're thinking about parking functions, because there's several points of view you could take. I will share 3 of my favorite of our results. They're all purposely chosen to be ones that required the computer in interesting ways. And then I'll wrap up by zooming out and showing you the scope of what we figured out rather than just these few favorite results. So first, the permutation part of the intro. When I think about a permutation, to me, a permutation is just a list. I'm not thinking about any bonus algebraic structure. And so I'm going to use S sub n for the set of all permutations of the numbers 1 up through n. And I have this here just to emphasize, I'm not using cycle notation or 2-line notation. A permutation is just a list, and we know there's n factorial permutations of size n. While I'm not using any algebraic structure here, it does help me to think about permutations in a visual way. And so here is how I would graph each of the 6 permutations of size 3. If the ith entry of a permutation is called pi sub I, we plot the points I comma pi sub I in the xy plane. For example, down here, the first number is 2, so I've plotted 1 comma 2. The last number is 1, so I've plotted 3 comma 1, and so on. So I'm not really visualizing permutations in my head in this list manner. I'm really thinking about this picture, whether it's written in a list or already plotted out for me. And here's a slightly bigger example, just to make sure the plot idea is familiar. Here's a permutation of size 9. You can see it's 9 dots living in a 9 by 9 square. The height of each entry tells you the value in that position of the permutation. So now that you have the same picture as me for how I'm thinking about a permutation, we're going to start looking for smaller permutations inside of larger ones. So there's that same permutation of size 9. And I'm going to pick just some of the dots to look at. For example, 3 of them just became orange. And if you ignore all the black dots and just focus on the 3 columns that have orange dots and the 3 rows that have orange dots, you have this picture on the side where the first orange dot was smallest, the second orange dot was largest, and the last orange dot was kind of the medium size orange dot. And that's the same picture as I drew for 132 a couple slides ago. So we say our permutation of size 9 contains this permutation 132 inside of it. That's not the only 132. There are other choices of 3 dots that make this small, large, medium kind of shape, but definitely it's in there at least once. We can also find other patterns. For example, there's 1, 2, 3, 4. It consists of picking 4 dots that go in increasing order. And again, it's not the only copy of 1, 2, 3, 4. but there's at least 1, 2, 3, 4 inside there. So our permutation of size 9 contains 1, 2, 3, 4. The opposite of containing is avoiding. So no matter how hard you look, you cannot find 4 dots here that go in decreasing order. And so the vocab is this permutation avoids the pattern 4, 3, 2, 1. So it's good to check you understand definitions by taking a big permutation and looking for smaller things inside of it. But that's not a research problem. That's a check your understanding problem. The research problem is to flip things around and start with the smaller permutation and ask questions about larger ones. So I could ask how many permutations of length n contain a specific pattern, or I could ask how many permutations of length n avoid a specific pattern. Of course, as soon as I've answered one of those, I've answered the other one because the sum of those two questions will be n factorial. And of course, the answer depends on what you're trying to contain or avoid. And for reasons connected to computer science, the focus has generally been on the set of permutations avoiding a pattern. And so that is the prereqs of patterns in permutations that we need to move forward. And that's the part that I've been thinking about for the better part of 2 decades now. And so now I'm going to introduce a different object to try to extend these pattern definitions.
And you're organizing an international conference on that topic coming up this summer, right?
That's true. So as a slight detour, there is an international conference on permutations that has been held annually for about 2 decades that was supposed to be at my school in 2020. And then we know so many things went virtual. We are planning for an in-person conference this year, yes. So if you like patterns in permutations and other things, I can share the link at the end of the talk. That's true. So that will be exciting. That's the permutation part. And now I'm going to switch to IO's focus, which is the parking function part, and we'll see how they mash up. So here's the official definition of a parking function that you would see in a book such as Stanley's Enumerative Combinatorics. It's a sequence of numbers. You're choosing from the numbers 1 through n for each entry, and you make a sequence of length n so that if you rearranged it to be in non-decreasing order, the ith entry would be less than or equal to I. But it might help to have a story to motivate what exactly is this doing and what does it have to do with parking. So the story is you have n cars and they're numbered 1 through n, and they're about to park on a one-way street where the parking spots are numbered 1 through n. And the first car has its own favorite parking spot. That's what A1 is. The second car has its favorite parking spot. That's what A2 is, and so on. This A1 through AN sequence is everybody's preferred favorite parking spot. So car A1 will go down the street and park in their favorite spot. Car 2 will go down the street, and if their favorite spot is available, they will park there. And if it's already taken, they'll go to the next available spot. And you don't get to go down the street twice. So car 2 will be fine unless both of them preferred the very last spot. If they both preferred the very last spot, car 2 is out of luck. This condition is really capturing which sequences of preferences will result in all the cars getting to park. And so as some examples, in black here, I have a couple sequences of length 5, and in gray below them, I've written them in increasing order. You can check that the ith entry is always less than or equal to I. So these are all parking functions. Here are some non-examples. There's still sequences of length n chosen from these digits, but you can see here the first entry is too big. So all 5 cars are going to try to park in spots 2 through 5, and that won't allow them all to park. Or here the third spot is too big, so too many cars are going to try to go for spots 4 and 5. Or here there's too much competition for the last spot. And so if this is a new definition, I just want to emphasize 2 things. There's a lovely argument that the total number of parking functions is n plus 1 to the n minus 1 power, parking functions of size n. And it's a cute argument worth looking up. I'm not going to spend time on it right now because I want to save time for the patterns. But what you should notice from this definition is every permutation of size n is also a parking function, because if all the cars prefer different spots, everyone's going to get to park. And so you can think of parking functions, at least in this context, as a generalization of permutations. Every permutation is a parking function, but then there's some bonus things that are parking functions but are not permutations. And so looking at parking functions just as words, lists of numbers, and thinking about patterns in those, that has been done. So there's a paper in 2009 by Vít Jelínek and Tufik Mansour who just looked at parking functions as words, and they were looking at a variety of kinds of words, but some of the results are about parking functions in this sense. And they determined all equivalence classes of patterns of length at most 5. That means they could put all the patterns of length at most 5 into groups of, if you avoid this pattern, you get this sequence. If you avoid this other pattern, you get the same sequence for number of pattern avoiding parking functions. So we're not going to think of parking functions just as words. We're actually going to borrow from someone else's work. And so a little more recently, in 2016, there's a paper of Jeff Remmel and Dun Chu, who they were really focused on ordered set partitions. But there was a kind of postscript to their paper that had one specific parking function result. So instead of thinking of parking functions as words, like on the previous slide, they thought of them as dict paths, where all the northward steps were labeled with numbers. And that was a bijection from parking functions to labeled dict paths. But once you have a labeled dict path, there's a many-to-one correspondence between dict paths and permutations. And so they said, okay, how many parking functions, when you go through this labeled dict path machinery and then to permutations, are associated with permutations that avoid 1, 2, 3. And so it's kind of one special result that appeared at the end of a talk and at the end of a paper about something else. And this was one of the last papers before Jeff Remmel passed away, and Dun Chu was his last PhD student. And we've been in touch with Dun. He said, yeah, I'm not working on that anymore. I switched focus when I got a new advisor to finish my work. If you want to roll with that definition, please do. And so we've kind of picked up where Remmel and Chu left off. I'm going to show you their machinery of thinking of parking functions as labeled dict paths. And then we will count parking functions whose associated permutations avoid a subset of the permutations of size 3. So I need to show you the machinery of how Remmel and Chu were thinking about parking functions. So here are all the parking functions of size 2 in the sense I introduced a couple slides ago. Remember, this first one means both cars like spot 1. This one means car 1 likes spot 1 and car 2 likes spot 2. And this one's the other way around. But here's an alternate way I could represent the parking functions. I could make a list of sets where the first set is the cars that like spot 1, and the second set is the set of cars that like spot 2. So here, both cars like spot 1, nobody likes spot 2. In each of these, you have one car liking each spot, and this specifically is car 1 likes spot 1, car 2 likes spot 2. Now here's where the dict paths come in. You're kind of front-loaded. Everybody could like spot 1 and it's fine. But at most one person could like the last spot. So there's actually a bijection where you take dict paths, thinking of them as north steps and east steps that stay at or above y equals x. And you label the north steps with numbers in column I are the cars that like spot I. So there's one dict path that starts with 2 north steps. That matches with the parking function where 2 cars like the first spot. And so this is the labeled dict path that goes with the parking function where everybody likes spot 1. There's one dict path that has 1 north step in each column, but it can be labeled in 2 ways. This is the picture for car 1 likes spot 1, car 2 likes spot 2. This is the picture for car 2 likes spot 1 and car 1 likes spot 2. And so you can actually take this block notation and think of the things in the ith set as the numbers in the ith column. The one catch I haven't mentioned yet is cars that like the same spot need to be labeled in increasing order as you go up the column. That's what makes this a bijection. So Jelínek and Mansour were thinking of parking functions in the sense of this first line. Remmel and Chu and now us are thinking of parking functions in this sense. And now you might see how I get a permutation associated with these. This is a bijection here. This is not a bijection, but it is a many-to-one correspondence. So if I just read the north step labels off the dict path, starting from 0, 0 and going till I get up here, that gives me my permutation. These first two are associated with the permutation 1, 2. This one's associated with the permutation 2, 1. And so that's the definition that we're going to work with throughout this talk. Let me give you a little bit bigger one to give you a little more time to digest what's going on. So here's a parking function of length 7. Here's the notation for, okay, cars 2 and 7 like the first spot. I can tell that because there's a 1 as the second number and the 7th number, and so on. Nobody liked spot 7. I can make a dict path that has 2 upsteps in its first column, 1 upstep, 1 upstep, 2 upsteps, no upsteps in this column, 1 here and none here. And then I've labeled the upsteps in each column with the cars that liked that spot. In the places where multiple cars like the same spot, notice the numbers are increasing as you go up the column. And so this parking function is associated with this permutation from reading off the labels, starting at the bottom of the page and working their way up. That's the key way to think about parking functions for this talk. And so our big project for the last 6 months is, instead of counting permutations that avoid a pattern, we're counting the parking functions of size n whose associated permutations avoid a pattern. And if you're familiar with the permutation literature, we lose all kinds of symmetries here, but other really cool things go on. For example, as a warm-up, let's avoid some small patterns of size 2. If you avoid 2, 1, as a permutation, that forces you to be the increasing permutation. Well, how many parking functions are associated with the increasing permutation? There are Catalan many, because every single dict path can have the increasing permutation written on it in our convention. And so the number of parking functions avoiding 2, 1 is given by the nth Catalan number. On the other hand, if you avoid 1, 2, as a permutation, you have to think about the decreasing permutation. And how many parking functions are associated with the decreasing permutation? Well, it's just this one, because remember, numbers in the same column had to appear in increasing order, and that's forbidden if we're avoiding 1, 2. And so every time your permutation has a descent, you have to go over to the next column. So there's some asymmetry here. Permutations that have a lot of ascents get associated with lots of parking functions. Permutations that have a lot of descents get associated with much fewer parking functions. And so now we have these definitions and we get to play, and we've taken care of avoiding things of size 2. So the 3 results I have to share with you in the rest of this talk are from avoiding sets of permutations of size 3. The first one I want to share with you is this: whether you avoid this triple of patterns or this other triple of patterns, you get a difference of Catalan numbers. First, let's think permutation style, and then we'll connect it to the parking functions. So this is a picture of a typical member of, let's see, this is length 7, of a permutation that avoids these 3 patterns. You can think about the role of each of these patterns. If you avoid 1, 3, 2, wherever the largest number is, everything before it has to be larger than everything after it. That's what 1, 3, 2 is forcing. Since we avoid 2, 1, 3, everything before the largest number must be in increasing order. And since we avoid 3, 1, 2, everything after the largest number must be in decreasing order. So permutations avoiding this triple of patterns look like your largest digits in increasing order, followed by the remaining smaller digits in decreasing order. And the permutations avoiding this other triple of patterns are quite similar. Notice we've just traded out 1, 3, 2 for 2, 3, 1. And so we still start with an increasing sequence and end with a decreasing sequence. It's just now the smallest numbers make the increasing sequence. The largest ones form the decreasing sequence. So as soon as you know the position of n, the rest of the permutation is determined. If you were just counting pattern avoiding permutations, you would say that there are n permutations of size n avoiding these. But we need to think about how many dict paths each of these permutations can be written on to understand the number of parking functions avoiding these patterns. And I'll point out all the ascents are front loaded. So this permutation has 2 ascents and then everything else is descents. This one also has 2 ascents and then everything else is descents. So I'm going to focus on the number of parking functions avoiding this triple of patterns, whose associated permutation behind the scenes starts with k minus 1 ascents. And the two boundary conditions are, what if you start with 0 ascents? That's AN1. If you start with 0 ascents, you only have this part of the picture. You have a decreasing permutation. And we've already seen there's only one parking function associated with the decreasing permutation. On the other hand, if you have as many ascents as possible, so we're talking about ANN here, you're talking about the increasing permutation. This part of the permutation isn't here, it's just all increasing. And we've already seen the increasing permutation can be written as labels on any Dick path. So the other boundary on this triangle of numbers is the nth Catalan number. And now more generally, for any k value between these, there's two cases. Either one car likes the last spot or nobody likes the last spot. And so we'll address each of these cases in turn. If there's one number in the last block of our parking function, then there's a nice bijection here. We can just say, okay, here was my parking function that had one number in the last spot. Let me delete it. And then of course, subtract 1 from these numbers so that you don't skip anything. But I still start with the same number of ascents and I just have one less number involved in my parking function. And of course, if I have this picture, I can reinsert the last block and add 1 to each of these numbers. This is a bijection between things in this first case that started with k ascents and things that still start with k ascents but involve one less car. So the first case, if we're dealing with A and k, and we know the last block has one element, is the same number of things as A n minus 1k. So now, what if the last block is empty? What if nobody preferred the last parking spot? Well, that's a different, more entertaining bijection. You can tell that the pictures on the left of each of these pairs have their last block empty because there's no numbers in the last column. And what we're doing here is identifying the last number before n and highlighting its north step and all the east steps immediately before it. So in this case, 5 is the n, and the north step right before the n is the 3. I'm taking this north step for the 3 and the 2 east steps before it. Or same idea here, maybe there's no east steps before it. I'm still taking the 3 and however many east steps are right before it. And then I'm kind of rotating that 180 degrees in the air, the red part, and inserting it before the last east step. So here, east, east, north with a 3 became north with a 3, east, east, or just north with a 3 stayed being north as a 3, but they moved from where they were before n to right before that last east step. When I do this, I've reduced the number of ascents at the beginning by 1 because I've taken something out of this increasing run at the beginning and moved it later. And so that's why the k minus 1 went down. I didn't change the length of the parking function, but now I can get any parking function, whether there's something in the last block or not. So this actually gives a bijection between case 2 here and the parking functions counted by a n k minus 1. And so we have a triangle of numbers here. We have 2 boundary conditions and we have this recurrence. And of course, it made sense to count these according to number of ascents. It made sense to look at the A and Ks, but I don't know that we would have found this recurrence without some help from OAIS. So we had actually brute force computed these A and K numbers and searched and found there are several things in OAIS known as Catalan's triangle. This is one of them. The sum of each row is the n plus first Catalan number. The rightmost diagonal in this particular version of Catalan's triangle is the nth Catalan number. And so since we were getting this triangle in OAIS with its rightmost diagonal missing, we were actually getting a difference of Catalan numbers. So it was thanks to this entry existing that we realized we needed to prove this recurrence. So that's my first result. And I know some of you think about pattern avoiding permutations. I think there's something striking if you try to make an analogy with what you'd expect in pattern avoiding permutations when you compare the last line of this slide to the first line of the next one. So here we were avoiding 3 patterns of length 3. None of them were monotone, and we got a difference of Catalan numbers. On my next slide, I'm avoiding 2 patterns of length 3. One of them's monotone, one of them's not. and I get difference of Catalan numbers again. But this will be for a completely different reason and using the computer in a completely different way. So first, again, I will think about the permutations avoiding these patterns, and then we'll connect it to the parking functions.
And Lara, is there a bijection between these two things that you know of?
Between the previous result and this one?
Yeah, it's just shifted by n, right?
Oh, it's the exact same sequence.
Oh yeah. So is there a bijection between them?
Well, wait till you see how I prove this one, and then we'll give you a better answer. The proof feels very, very different. So here is a picture of a typical permutation avoiding these two patterns. Because we're avoiding 2, 1, 3, here's the smallest number. Everything before it is bigger than everything after. And because it avoids 1, 2, 3, everything after the 1 is in decreasing order. So as soon as you identify the 1, you know that you kind of have in the bottom right corner of the picture a bunch of numbers in decreasing order, and then everything to the left is bigger. And you can kind of recursively fill this in. I'll call the stuff in red an interval, the stuff in blue an interval, the stuff in black an interval. You end up with a bunch of intervals along the diagonal of this picture. Each interval might just have 1 dot, or it could have more dots. But if it has more dots, it's always the smallest one, followed by the others in decreasing order. So notice where the ascents are. In the previous result, all the ascents were at the beginning, followed by descents. Here, the ascents can be between the first 2 numbers in an interval, and that's it. If you're later in an interval, those are descents, or if you're jumping from one interval to the next, that's a descent. So the only place you can have an ascent is at the beginning of an interval. That means the only place where you could have 2 numbers in the same column is if they're the first 2 numbers from an interval of the permutation when you go to write it on a dict path. So I don't have a bijection between this and the previous one to articulate. I do have an alternate way to represent the ways these permutations get written on dict paths. And it's going to be a special arrangement of dots and parentheses. So there's going to be 1 dot per number in the underlying permutation. And then there's going to be some amount of parentheses, could be as few as 1 parenthesis pair or as many as n parenthesis pairs. There's going to be 1 parenthesis pair for each interval of the permutation. Like on the previous slide, there was the red interval, blue interval, black interval. That would have 3 pairs of parentheses involved. So the left parentheses will tell you where the start of each interval is. And the right parenthesis will tell you, well, did each number end up in its own column in the dict path? Or did I put the first 2 numbers from the interval together and then have to have an empty column later? Let me show you some specific examples of this. Here's the same permutation from the previous slide. I've color-coded the numbers to match the intervals from the previous slide. And if I made it into a parking function where everybody was in its own block, I would get this arrangement of dots and parentheses. So I have 8 dots here corresponding to the 8 numbers. I have a left parenthesis at the start of each interval. So at the very beginning, before the 5th dot and before the 6th dot. And since each pair of parentheses just encloses 1 dot, everybody is in its own column in the dict path, or in other words, everybody's in its own block. What if I took one of the ascents and put them into the same block? Well, the black stuff and the blue stuff looks the same. The red interval still starts here, but I've moved the right parenthesis here to indicate that there was an empty set after the block with the 2. Or what if I put the 5 and 8 together and I put the 1 and 3 together? Since I have 2 blocks of the parking function that have 2 elements, that must mean there's 2 empty sets later. And so I have an empty set after the 3, there's that right parenthesis. I have an empty set after the 2, there's that right parenthesis. So these are some strange arrangements of dots and parentheses, but switching from thinking of the 1, 2, 3, 2, 1, 3 avoiding parking functions to the dots and parentheses notation is what allows me to count them. So here are what the dot and parenthesis arrangements look like of size 1 and of size 2. Again, the number of pairs of parentheses corresponds to the number of intervals in the underlying permutation. And then we get this wild recurrence. And it comes in 2 cases. we're going to condition on how many dots are inside the first pair of parentheses. So you have to start with the left parenthesis because every permutation starts with some interval. That parenthesis and its matching parenthesis either enclose one dot, that's what's going on in red, or it encloses two or more dots, that's what's going on in blue, and that's the role of I. I is how many dots are inside that first pair of parentheses. So in the first case, the red case, you could have j more dots before the next parenthesis. This would correspond to the first interval of your permutation having size j plus 1. J could be as small as 0 or as big as the rest of the permutation. And then you need to recursively fill in another dot and parenthesis arrangement here with the remaining n minus 1 minus j dots. And so that's the red case. In the blue case, j is doing the same thing. It's how many dots are here after this parenthesis, but before the next one. Also, inside the initial parenthesis, we can have k dots before there's another parenthesis. K has to be at least 2, because if k was 1, we'd just have 1 dot inside the first parenthesis and we'd really be in the red case. And so as long as we recursively fill in this part and sum over all reasonable values of j and k, that's what's going on in the blue case. So that's a wild recurrence with this triple sum here. But remember, I had a conjecture based on some brute force data. I was conjecturing that this is a difference of Catalan numbers. And the best explanation we have is, well, 1 and 3 match up with differences of Catalan numbers. And now if I make Maple assume that the stuff in red and the stuff in blue everywhere we see an F matches this formula, Maple can take the summation identities it knows and massage this right-hand side down and realize it does simplify to a difference of Catalan numbers. That's the cleanest explanation we found for this one. So it's a different level of intensity compared to the previous result for the same sequence. And this really is the computer wrote the induction for me.
But it would be nice to have a more insightful combinatorial proof. But
oh, absolutely. But we don't have it yet. So we can prove it's this sequence. But open, is there a different way to approach it that explains difference of Catalan numbers in a less nested summations kind of way?
And you have no bijection with this, and the previous nope. Problem was easier, right?
True. The previous problem was easier. We were avoiding 3 patterns, so it was more restrictive in some sense.
Yeah.
So yeah, it was friendlier to deal with those permutations because all the ascents were loaded at the front. This gets way more complicated when the ascents are spread differently throughout the permutation to connect it to the parking functions.
Another question, instead of this messy triple sum, can you do it directly in terms of generating functions?
That's a good question. I don't know the answer to that yet. I just know this is a different level of intensity and it doesn't match. We haven't found a way to look at them that matches that Catalan triangle from the previous result.
No, so beautiful. Don't get me wrong. I love ugly proofs. Thank you.
I would say it's a different flavored proof, and I felt really good that the computer really was a collaborator here.
It's very fitting for this seminar. Thank you.
That's how I chose it. So excellent. So those are my first 2 results. And the last one is also thanks to OAIS, but OAIS inspired us to do something different. So the last one I'll share today is a different sequence. It's a very nice sequence. And we would have never realized what bijection to look for without this OAIS entry. So if you look at—
I'm glad to hear that.
So yes, OAIS has been inspirational throughout this project, and just wait till you see the wrap up part, Neil. I think you'll enjoy it.
Excellent.
So for this particular one, I recognized these numbers before OAIS because I've done a bit with trees. I knew this was the number of ternary trees. I have not found a compelling reason why parking functions avoiding these patterns match with ternary trees, but the OAIS entry introduced me to non-crossing trees. And it turns out there's a bijection between parking functions avoiding 231 and 321 and non-crossing trees. So what do the permutations look like? Well, they're a 90-degree rotation of the ones from the previous slide, which totally messes with where the ascents and descents are, which totally affects the number of parking functions because ascents allow you to have more ways to label the dict path, descents give you fewer ways. So here is what's going to happen. I ultimately need to show you how to connect these parking functions to non-crossing trees. But our parking functions are really dict paths with some extra labels on them. And non-crossing trees are really rooted ordered trees whose vertices are placed on the perimeter of a circle in such a way that the edges don't cross. So I'm going to start with a simpler bijection between kind of the unadorned things. I'm going to show you a bijection between dict paths and rooted ordered trees. Those are both Catalan objects, so you may know many bijections between them. I'll show you the one that's particularly helpful here. And then I'll show you how labeling a dict path corresponds to a way of taking the corresponding rooted ordered tree and folding it up around a circle. And so it really is, if you understand the first bijection, then all the ways to label an object that you're about to run through the first bijection correspond to all the ways to fold up the other object from the first bijection. So here's a dict path and a rooted ordered tree. One canonical way to see that dict paths are counted by the Catalan numbers is to highlight the first north step and then highlight the first east step that returns to the y equals x line. And then you've got a smaller dict path over here in blue. You've got a smaller one up here in green. And of course, the red step could have been anywhere from down low to up high. You sum over all possible positions, matches the Catalan recurrence. A way to see that with the trees is to take the rightmost edge coming out of the root. That's what's red. And if you delete it, you end up with this tree with blue edges over here versus this tree with green edges over here. And you can kind of recursively follow things to check. This actually is the dict path that matches with this tree in this bijection. This just one path going down from the root tree really matches with the zigzaggy dict path. And this tree over here really matches with this dict path up here. I'm going to take the exact same bijection, but show you a slightly different way to organize it. So same dict path, same tree, but let me start with the tree for a moment. So in the tree, I'm going to start with the root and say it has two children there, well, and I'm going to focus on the edges. It has two edges descending from it, A and B. A and B correspond to the two north steps here. Then I'm going to go to visit the subtrees of the root one at a time. I'm going to go down to this one and read through all of it. I'm going to go then to this one and read through all of it. So every time you read an edge coming from a root, that makes a north step over here. And every time you go to visit the root of a new subtree, that makes an east step. So if we start at the root, it has two edges coming out of it. That's the two north steps on the right. Now I say, okay, cool, I have registered all of these edges. Let me go to this subtree. I'm at a new root, so that's a east. This vertex has one edge coming out of it. That's the blue north on the right. And that's it. So now I'm investigating the tree that's rooted here. That's an east because I'm at a new subtree. One edge coming out of it. That's the green north step on the right. Now I'm ready to investigate a new tree. So that's an east. There's nothing there. So now I'm ready to investigate a new tree. That's the second east in a row. Two edges coming out of it. That's the pinkish purple north steps in the dict path. When I go over here, that's an east. One north step. When I investigate below this, that's an east. When I investigate below this, that's an east. This is the exact same bijection formulated in a different way, where it points out that north steps that are in the same column match with edges that are emanating from the same parent vertex. So now I'm going to show you how I will take a dict path and label it to avoid our patterns. I showed you a picture of a 231, 321 avoiding permutation earlier, but here's a characterization that's particularly helpful. Notice that based on these two patterns, the digit D has to be either first or second among it and all the larger digits. For example, 1 has to be the first or second digit in the whole permutation, because if it was third or later, you would make one of these patterns. 2 must be first or second among the digits 2 through n. 3 must be first or second among the digits 3 through n. So let's start labeling this dict path so it follows this characterization. And also remember that numbers in the same column have to go in increasing order. The characterization up here says 1 must be first or second in the whole permutation. But the fact that we start with a column with 2 entries tells me 1 actually has to go first. If it was second, this red column would not be in increasing order. So I have 1 and a mystery number in the first block. Now 2 must be first or second of the remaining digits. And because we're kind of at this between blocks kind of situation, I really do have 2 choices for 2. It could have replaced the question mark and now I don't know what's here, or it could have gone here and the question mark stays put. Those are my 2 options for 2 must be first or second. Notice we got 2 choices when we were about to deal with a block, a column with just 1 number in it. For the sake of having space on my slide, I'm just going to pick one of these to continue playing with, and the second one would be similar. So let's look at this one, and we're about to have a block of size 3 coming up. How many choices do we have for filling in this? Well, we know these 3 numbers are in increasing order. 3 must be first or second among the things that don't have numbers yet. So 3 could go where the question mark is, or it could go here. And so if 3 goes where the question mark was, we have 4, 5, and a number to be named later in green. If 3 goes here, you can say 4 is first or second of the remaining spots. So maybe 4 goes here, or maybe 4 goes above the 3 and 5 goes here, or maybe 3, 4, and 5 go in green and I still have a mystery number here in red. The point being, when there was about to be a column of 3 numbers, I had 4 choices. I could put the first, second, or third smallest remaining number in place of the question mark I had before, or I could leave the question mark alone and put the 3, 4, and 5 here in green. For the sake of having enough room on my slide, I'm going to just pick one, but the other 3 cases are going to be similar. Here, I'm about to have a block of size 1. And so again, I have 2 choices. 6 could go in place of the question mark, or 6 could go here. And then as soon as you decide where 6 is, the 7 will go in the remaining spot. So to summarize, the number of parking functions I could write on this particular dict path is 16. I didn't have any choice with the red block. It had to be 1 and something bigger, but I had 2 choices when a block of size 1 was coming up. I had 4 choices when a block of size 3 was coming up. I had 2 choices when another block of size 1 was coming up. So 16 different parking functions go with this dict path. Through our bijection between dict paths and trees, this dict path goes with this tree. I claim similarly there are 16 ways to fold this tree so that its vertices are on the perimeter of a circle and its edges do not cross. So let's see if we can understand why. Here's that same tree. And remember, these are rooted ordered trees. So there's a sense of left and right. And on the circle, my sense of left and right will be read the things in counterclockwise order, and that's how you read from left to right. So if this black vertex is the root, this A is pointing to the leftmost thing in terms of that root, and B is pointing to the rightmost thing in terms of that root. I claim for this particular tree, these are our only options for A and B, because B is the rightmost edge in this tree. So B is pointing to the rightmost vertex over here in terms of this root. And then A either needs to go over here or over here, because everything in this subtree below A is a connected graph. And if you try to put it on A elsewhere, that connected graph is going to cross over A. And so this corresponds to the 2 choices we had when we had gotten to the red and the blue blocks together on the dict path. We have 2 choices here because we're about to have a generation of just 1 edge coming up on the tree. We'll get more into detail on that in a second, but let's continue trying to fold this tree around. I picked this start for a moment where B is going here and A is going here. And we're thinking about the options for C. It might seem like there are 5 choices for C, but one of them has a problem. You can see it because of the remaining vertices. D must point to the first thing going counterclockwise, and F must point to the last vertex going counterclockwise. And so as soon as you decide C, you know where D and F go. And maybe you see which one of these has a problem now. If you still need to put E and G in the picture, this one down here has a problem because wherever you put E, G will cross over C. What's really going on here is we have 4 choices because the next generation below C has 3 edges, and either C can fold to the left of all of this, that's the first picture. It could fold to the right of everything below it, that's the last picture. It could go between D and E, and that's what's going to happen here. Or C could fold in between E and F, that's what's going to happen here. And so we really do have 4 choices because a generation of size 3 was coming up. And that matches with, we had 4 choices when a block of size 3 was coming up in the dig path. And so I'm going to use the position of C relative to its descendants to decide, should I have used the 3, 4, or 5 in place of the question mark, or leave the question mark alone when I was filling in the dig path. Let me get one tree done out in its full glory. I was never going to get 16 on one slide because it's just too small a font. But here is a copy of this tree folded around a circle with non-crossing edges. And here's the corresponding dig path labeled as a pattern avoiding parking function. If you were thinking about labeling this dig path one block at a time, you know the first block is 1 and a mystery number. The position of A is going to tell me what to do with that mystery number as I go to fill in the blue block. If you focus on the vertex that A is pointing to as the root and read counterclockwise, you notice A appears to the left of C, reading in this counterclockwise way. So A is to the left of its one subtree. And since it's to the left of one thing, I'm going to use the first smallest remaining number in place of the question mark. This question mark turned into a 2. And now the question mark is in my new blue block. The position of C is what's going to tell me what to do with this question mark. So C was pointing to this vertex here. I know left and right will feel strange because this vertex is on the bottom of the circle. But if you read counterclockwise around, you first encounter D, then C, then E and F. So in this counterclockwise, like turn your head upside down orientation, C is to the left of 2 subtrees. And so the question mark will get replaced with the second smallest remaining number. So 3, 4, 5, 4 is the second smallest remaining number. This question mark turns into a 4 and the green block becomes 3, 5 question mark. The position of E is what's going to tell me what to do with this question mark. E points to this vertex here. And if you read counterclockwise around, you encounter G first, then E. E is to the left of 0 subtrees, so I leave the question mark alone and put the 6 here, and ultimately the 7 here. So really, you have this underlying Catalan bijection between dig paths and rooted ordered trees, and the labelings of the dig paths so that they avoid 2, 3, 1 and 3, 2, 1 correspond to ways to arrange the rooted ordered tree in a non-crossing way around a circle. So that bijection, again, never would have found it without OAIS. I don't know how to biject these with ternary trees, but I learned more about non-crossing trees thanks to that entry. And so to wrap things up here, I want to show you the big picture of our project. I showed you just 3 results, but what Ayo and I have been doing for the last 6 months is counting parking functions avoiding any set of 2 or more permutations of size 3. And so avoiding 4 or 5 things is more restrictive. Here's the chart of avoiding 3 patterns of size 3. Every single one is in OAIS for beautiful combinatorial reasons. You saw the proof that goes with this green line, but we've got odd numbers, we've got triangular numbers, central polygonal numbers. Some of these have fun things to do with trees. We've just about got all of these knocked out. If you avoid a pair of patterns, that's harder. And you saw my bijection argument in the second green row. You saw my computer induction argument in the first green row. And you get some new entries too. We've just about got these knocked out. What happens when you avoid just one pattern? That's where the adventure that I'd like to invite you, if this interested you, is to think about. So this was all inspired by this first line, the result of Remmel and Chu, which appears as like a postscript in a preprint. Their result is a nested sum of fractions involving binomial coefficients. It's not in OAIS, but it's the result that got us thinking. Brute force is how we got this data. 2 of the other sequences that show up, complete mysteries, and this one has a description. It's a newer sequence in OAIS. I looked up what a multi-parking function was 6 months ago and it made sense, but the paper that explains this whole description is way more algebraic than my experience. And so if these are meaningful words to you, I invite you to come think about this problem. And that's what I've got. So thanks for listening.
Lara, can I ask a question?
Thank you very much.
Lara, a quick question.
This ends the official part of the talk. Robert, please stop recording, but people are welcome to stay and ask unofficial questions. Go ahead, Neil.
I wanted to say that the sequence the 3n choose n divided by 2n plus 1. If you start off with the Catalan numbers and then look at that one and generalize it, these are called generalized Catalan numbers, right? And they come up in a lot of different places. So you might look at what happens if you go from 3n choose n over 2n to 4n choose n over 3n plus 1 and so on, and see if there's anything there that looks familiar to you, because this is all part of the big picture, you know, generalized Catalan numbers.
Actually, one of these sequences, I'm trying to think which one, is the super Catalan numbers too. There's all kinds of wild Catalan friends going on in these sequences.